Well, when you exceed your octet, you can have more than 4 things. And so there are 5 thing shapes as well. PCl5. So in this case, you've got a phosphorus, and we've seen this one before, but I'm going to put the chlorines with just the one unpaired electron to simplify our drawings. We'll pair. We have to break up a lone pair, but we can do that because it's third row or later. 5 things cannot spread evenly. Instead, you get 2 domains. You get an axial going up and down, and you get an equatorial going around. From the axial to the equatorial is right angles. They are 90 degrees. But between the equatorials, they are 120. And so this is the farthest you can get things. If you have 5 things and they are 5 atoms, what shape does this look like? It kind of looks like a triangle again, going up to a point, but also going down to a point. This looks like 2 pyramids with a triangle base. This is Trigonal Bipyramidal. It is a bipyramid with a triangle that is the connecting. Let's do SF4. So in this case, I have sulfur with 6 electrons. Fluorine, I'm going to put just the one unpaired electron on fluorine for simplicity. We would pair, and then we'd have to break up one lone pair. This is going to result in 5 things being around sulfur. A lone pair and 4 fluorine atoms. The bonds coming off of them there. Well, I'm going to arrange things as I arrange for 5. Question is, where do I put them? If I put that lone pair in the middle, that forces my fluorines axial. If I put that lone pair axial, well, that changes our shape quite a bit. One of these is going to look like a triangle going down to a fluorine with a sulfur in the center of the triangle, where the other is going to look more like a long object coming off a stand in the middle. Your electrons, because they're not reaching out to make a bond, they're stuck on the atom, they're actually physically closer than we normally would expect. They don't go as far away because they're not being drawn out towards another nucleus. The result is they have a bigger effect on repulsion than other atoms. And so you want your lone pair to be as far away as it can be, and your option is either 2 right angles and 2 120s, or if it was on top, it'd be 3 right angles and 1 180. Right angles are a lot closer together than 120s. The net result is that it is easier to put it equatorial. If given the option, your lone pairs will choose to be equatorial. That is, just gets them farther apart. Well, another way to kind of draw this would be, tip it on its side. And so this would be fluorine here, fluorine there, fluorine here, and a lone pair going up. Well, this kind of looks like a seesaw, and that's the name for it. If you have 5 things, 4 atoms, 1 lone pair, it is a seesaw. Sometimes you'll see distorted tetrahedral for people who don't like the name seesaw, but it's pretty much stuck. Basically, you can imagine one of these ends going down, this one going up, and then going back the other way. It's like the old playground toy. You can also do IF3. It is possible to put extremely electronegative fluorine on other halides. In fact, you can get chlorines on bromines or chlorines on iodines as well. In this case, though, let's just draw iodine with 7. Fluorine, I'll just put the 1 relevant unpaired electron from our fluorines. And so I'll pair once, and then I have to break up one of the lone pairs. But iodine is third row or later, and so it can do this. Net effect is I'm going to have 5 things. My lone pairs are going to go around the middle. In fact, let's put them on these two. And my fluorines are going to go on the sides. When you just look at this, well, it looks like a shape that is connected at the middle. And hey, you can kind of make it this, turn it on its side. This is T-shaped. This is a molecule that does have right angles between the atoms. In fact, those are the only angles it's got. When you have 5 things, 3 atoms, 2 lone pair, you are T-shaped. And finally, you can get things like Xenon Difluoride. You can also get IF2 minus if you want an anion, things like that. Let's do this one. Xenon Difluoride. Well, xenon has 8. Fluorine, we'll put the 1 relevant. Now, we don't normally think of noble gases as reacting, but xenon actually can. Fluorine is so electronegative, it can react with xenon. The guy who discovered it won a Nobel Prize for it because nobody had ever got a noble gas to react before. But it took us quite a while to make fluorine gas safely. So once we had, they noticed that they reacted. We break up one of those lone pairs. Well, that's 2 fluorines and 3 lone pairs. My lone pairs would go around the middle to spread out. My fluorines go up and down, which means this just looks like a straight line. It's linear. 5 things, 2 atoms, 3 lone pairs. Makes it a linear molecule. So this is quite different than carbon dioxide, which was linear for only having 2 things, but we can recreate similar geometries between the atoms if we have the right lone pair combinations. And 6 things. SF6, you'll have a sulfur, and you'll end up with just 6 fluorines around it. All of these are right angles. Right angle, right angle, right angle, right. Only ones that aren't are opposite. 180 degrees on the opposites. These are pretty crowded together, but it is a possible shape to make, and this is octahedral. Why is it called that? Well, it's because you get 8 faces. You get a triangle here, that's a face. You get a triangle here, that's a face. You can do one up front. You go from the top to these front ones. You can do one in the back. And then you can do it again on the bottom. Basically, if you have an 8-sided dice, well, there's a point up and down and 4 around the middle. So it gets the name octahedral. When all 6 are atoms. But not all 6 have to be atoms. BRF5. You've got bromine with its 7 electrons. You've got 5 fluorines with their 7 electrons, but we'll show just the one unpaired. Pair that and then break up 2 lone pairs, where you're going to get 6 things around bromine. Well, 6 things are going to arrange so that they're right angles from each other. Doesn't actually matter where your lone pair is. It's going to be at right angles to 4 things and 180s from something else. So it's irrelevant where we put that lone pair. It's going to have exactly the same angles to other things. We tend to draw it on the bottom because this then lets us see a square base all going up to a single point. Well, when we had a triangle base going to a point, it was trigonal pyramidal. If I have a square base going to a single point, it is square pyramidal. This is 6 things, 5 atoms, 1 lone pair. Xenon tetrafluoride. 8 electrons, I get my fluorines, the 1 valence, unpaired electron. Break up lone pair, break up a lone pair. This is going to give me 2 lone pairs and 4 atoms. At this point, again, it doesn't matter where you put the lone pairs, except that now with 2 of them, they need to be on opposite sides. So they could be top and bottom, they could be left and right, but we tend to draw them top and bottom for conventional sake. When we have this, I've got a square going between my equatorials, and there's no up or down. There's just a xenon sitting in the center, and 4 things going out to make a square. This is a flat plane. This is a square planar. So our Lewis structures can quickly indicate a molecule and its bonding. But to know what the shape is, we have to apply the idea of VSEPR theory. These electrons are going to push each other apart in order to spread out, and these are the shapes that we see. When these electrons push to spread out, well, there's only certain angles that will get them farthest from each other, so they're going to end up at those angles. These are those predicted sets. And so for 6 things, we expect them to all be 90 degrees apart, unless they're on opposite sides. For 5 things, we have a choice of 90 or 120, depending if they're axial equatorials. For 4 things, we expect them all to be 109.5. For 3 things, we expect them all to be 120. And for 2 things, we expect them all to be 180. Each of these, depending on the combinations of atoms versus lone pairs being used, has a slightly different name. But these are very reliable in terms of what we actually find for molecules. VSEPR theory is very good at letting us determine the shape of a molecule from a quick Lewis structure.